All right, let's solve another example. This time it is question 101. We are given a circuit. It is a parallel circuit. We have a power source, the positive side upward, negative side downward, and three resistors in parallel, R1, R2, and R3. I already have my Ohm's law table. It is the same table as in the previous example, same logic. Let's read the question. So in this question, basically, we are given some value. We are told that the voltage by the power supply, so V, is 12 volt. Now note, by the way, we got our equivalent resistance. That's always the voltage on the equivalent resistance. Even though we don't know the equivalent resistance now, we do know the voltage here. Okay, R1 is 1 ohm. So R1, 1 ohm. R2, 6 ohm. R3 is 13 ohm. All right. We are asked, part A, what is the total resistance or equivalent resistance? Part B, find the total current. Part C, calculate the current in each resistor and show these add to equal the total current output of the source. Part D, calculate the power dissipated by each resistor. So the first thing we should do is calculate the equivalent resistance. So I'm kind of missing some place here. I'm not gonna write down the formula. It is the same formula as shown in the summary. So we can find the equivalent resistance using that formula, and I get an equivalent resistance of 0.804. That's the equivalent resistance. And basically, we can now find what is the current, and I get 14.92 in this case. So 14.92 amp. Now, in this problem, the current does not behave the same way as in a series circuit. The current goes from the source, and that's the total current going through the source, by the way, 14.92. It gets to the first junction, and then it's split. Some of it goes into R1. Some of it goes in to the right. Then there's another junction. Some of the current is going to R2. Note, the remaining current is going to R3. Once the current is here, the charge over here, they are not going back through the resistance. The charge always follow the path of least resistance. All right? So, and then the charge of R3 combined with the charge of R2, and then they go back to the other junction, and all three charge, the charge of each of the three resistance combine again and goes through the source. All right. Now, because it is a parallel circuit, if we look at the assumption we use at the beginning of the chapter, the voltage on each wire is the same. There's no voltage drop on each wire. So let's set a value for this one. Let's say it is 0 volt. Now, often, by the way, if you only got one power supply, you can decide that this value is 0 volt, it will work. The only thing that matters is the difference in voltage. It does not matter where you decide that your 0 is. Like I mentioned in the introduction, we use the ground as our 0 generally, but the ground there is some electrical charge, so there is a certain voltage on the ground. But because we can only measure a difference, it does not matter. As long as we are consistent with when we decide where our 0 is, we keep it that way for the remaining of the problem. Now, there's a 12 volt over here. What that means is, once the charge goes through the power supply, they get a bump in 12 volt of energy, 12 volt. And this wire, there's no voltage drop in the wire. What that means is, right away, we can find the voltage on each resistance. Well, it is 12 volt, 12 volt, 12 volt. 12, 12, and 12. Just like I said in the introduction, the voltage is the same. This is the reason why. Okay, right away we can find the current. So R1, 12 amp, 2 amp in R2, and I'm gonna calculate just to make sure I got this one right. Yeah, so it's 0.92 amp in R3. Note, if you add the current through R1, R2, and R3, they add up to the current going through the source. Like I mentioned in the introduction, charge are conserved. There's no charge added, there's no charge destroyed in our model. All right? So then the current going through R1, R2, and R3 have to match the current going through the power source. All right, last step, we need to find the power dissipated by each resistance and the power at the source. So power through each resistance, this one is 144, this one is 24, and this one over here is 11.04. This one over here is 179.04. If you add up these, just to make sure they match, and that's a good trick to know if you did not make a mistake, by the way. They need to match. And yes, if we add these three power, we get back to the power supplied by the source. In some sense, even though it's not written on the Ohm's law table, the power from the source over here is really the power supply by the battery in this case. These are the power consumed. So they have to match at all time. All right. So that's it for question 101. In the next video, we are going to start tackling mixed circuit and the strategy we can use in order to solve more complex circuit. All right. So see you in the next video.